Good morning, student. So, welcome to Urban Pro. In today's session, I'll be discussing on Biot-Savart law and Lorentz force. Okay, what is Biot-Savart law? So, before going into Biot-Savart law, let me discuss one more thing. See, suppose this is a current carrying wire. Okay, this is a current I is being flown through this wire. When a current flows, a steady current flows, a magnetic field is produced around it. Okay, so these are the points I'm drawing randomly. At every point around it, magnetic field is produced. Okay, magnetic field is produced around a current carrying wire. Now the Biot-Savart law is all about the magnitude and direction. It's all about magnitude and direction of magnetic field produced by a current carrying conductor or wire. Okay, current carrying conductor. Fine. So suppose we are interested at this point. Suppose the point be P. We want to calculate, according to Biot-Savart law, what will be the magnetic field at point P, not due to the entire conductor. It is, the law says, suppose I take this an elementary current carrying wire. This is a current carrying wire, but I take, the law says, suppose this is a element of the conductor and the length is, suppose the length is dl, elementary length dl. The length is dl and the direction is along the current through which it is flowing. Okay, amount of current is I. And suppose the line joining the element and the point at which we will find the magnetic field is this. Suppose it is represented by vector R. Okay. According to Biot-Savart law, it is the magnetic field is represented by dB, that is elementary magnetic field, small magnetic field. That is, it is the magnetic field due to the segment dl. Okay, that is why it is represented by dV. dB is proportional to the current proportional to dl cross R, inversely proportional to the square of the distance between the elementary point and the point at which we want to find the magnetic field. Okay, so see, I made a mistake here. This is not actually R vector, it is R cap, means it is unit vector. Okay, if we combine these three relations, we will have dB proportional to I dl cross R vector R cap by R square. Now, if we replace this proportional relation, it will become equal sign, and the proportionality constant is actually mu naught by 4 pi. Mu naught by 4 pi. And the same thing, I dl cross R cap by R square. This is the vector form of Biot-Savart law. This is vector form. This is vector form. What will be the scalar form? The scalar form will give only magnitude, not direction. That is, dB is equals to mu naught by 4 pi I dl sine theta by r square. Simply, I hope you know, here we have only dl cross r. A cross b means a b sine theta, where theta is the angle between dl and r, isn't it? So let me draw here what is r. R is here. This is the angle between dl and r. Okay. See, if we focus on the direction dl cross r, let us recap once again about the a cross b. A cross b. Suppose this is a vector a and this is one more vector b. Now we want to find a cross b. That is, how do we do this? We curl our four fingers except the thumb. We curl in this direction a cross b, that we will start from a and we towards b. We will curl our fingers except thumb. We will curl our four fingers from a to b and we will extend the thumb. We'll try to keep it 90 degree with all the four fingers, and then the thumb actually directs the direction of a cross b. In this case, the a cross b is, as I can see, it is out of the plane of the paper, out of the plane of the paper. Here in this case, we are not using with paper, it is screen actually, out of plane of the screen. Okay, that we denote by how? By a dot within a circle in this case. So let us see what will be the direction of the magnetic field at point P due to this current carrying wire. Here dl cross r, dl cross r. As we can see, dl is somewhat in this direction. This is dl, and r is what? This direction. Suppose this is r cap. So dl cross r, if we curl our four fingers from dl to r, the thumb will direct into the plane of the paper, that is into the screen, and we denote it by how? By a cross within a circle. Okay. So here, in this case, it is actually into the plane of the paper, into the plane of the paper. Now, if we just alter the direction of the current through this conductor, what will be the direction of the magnetic field at point P? Let us draw one more figure for the same. Here, I'll alter the direction of the current. Look very carefully. I am erasing the arrow representing the direction of the current. It is really tough to erase this, but point eraser. Okay, you have to compromise with the drawing. I hope it's now fine. Here what I have done, I have just altered the direction of the current. So the dl vector is changed. Here the dl vector is changed in the opposite direction, that is in it is in this direction now. Now what is dl cross r? What is dl cross r? We will curve our four fingers except thumb from dl to r. Then if you see, look carefully, you try it by yourself only, you will find that it is out of the plane of the paper. It is out of the plane of the paper. So here we have to conclude that I mean, we can take conclusion that when the current is just altered, the direction of the magnetic field at every point gets altered. It is oriented by 180 degrees. Okay. Okay. Now we'll discuss some applications of the Biot-Savart law. Some example will discuss simple example. I mean, the introductory examples will not go into deep. Suppose this is a current carrying conductor and it is a special, that is, it is a circle. The current that is being flown through this circuit is I, and this is the center. This is the center of the circular coil. Current I is being flown. We have to find, not we have to, we are going to find the total magnetic field at the center. Suppose the point is O. Okay. We are going to find okay, wait. What we want to find? We want to find magnetic field at the center of the current carrying coil. Okay. Suppose the radius of the coil be r. Okay. How we will find the total magnetic field at the center? We will take some elementary current is I is only. Suppose we take an elementary elementary current. Current is flowing I. The length is dl. The length is dl. So due to this segment, the magnetic field at the center dB, I am not going into the direction, dB is equals to mu naught by 4 pi I dl sine 90 degree by r square. Why 90 degree? What is theta? As I told, theta is nothing but the angle between the dl and r. Theta is angle between dl and r, isn't it? dl and r. Here in this problem, the dl is in which direction? It is in this direction. It is the direction of dl. What is the r? R is r is this one. This is r cap. What is the angle between this dl and r? It is nothing but 90 degree. So the magnetic field due to this elementary dl is nothing but mu naught by 4 pi I dl by r square. What will be the direction? Again, use your four fingers and thumb. That will give you the direction. I am erasing this for the clarity of the drawing. See, dl cross r, what will be the direction? I am doing, this is dl, this is r, so dl to r, this is out of the plane of the paper. Due to this segment, it is out of the plane of the paper, so I am representing it by a dot only. Okay, I am not writing much. So now take one more segment here. Here also the dl is along this. This will be the dl. This will be the r. The direction at the point, the direction of the magnetic field due to this dl segment at the origin or at the center will be the same as that we already calculated. The magnitude will also be the same, isn't it? For every segment we consider, for every segment, the direction and the magnitude of the magnetic field at the center of the coil will be the same. So what will be the total magnetic field at the center due to the coil? This is nothing but the summation of dB. Here, what are the constants? Here we see, except this dl, everything is constant. Mu naught by 4 pi I by r square, this is constant. Only variable is dl. So we will write the mu naught by 4 pi I by r square part out of the summation, and we'll keep the dl inside the summation only, and this will give mu naught by 4 pi I by r square. Now you tell me what will be the value of this dlr. See, summation of dl, what does it mean? All the summation that is all the dl part, all the elementary part, we have to take just the sum of all the elementary part in the coil. That will nothing but, this will nothing but the sum of dB, sorry, the dl is nothing but the circumference of the coil, which is 2 pi r. So we will write 2 pi r in place of the sum of dl. So finally we will have mu naught by 4 pi I by r 2 pi. Intentionally I written here 2 pi. I could have divided by, I divide this 4 pi by 2 pi, I could have written 2, but intentionally I write mu naught by 4 pi I by r 2 pi. Why? It has a physical significance actually. What is that? See, at the center, the total circle obtained an angle that is nothing but 2 pi. We will use this information or message in the next problems. These are basically special cases. Special cases. What are these? Suppose I ask you, I give you a semicircular current carrying conductor. This is a semicircular current carrying conductor whose center is this O of radius r, and a current is flowing through this I. What is the magnetic field at the center O? Just focus on how I am writing. This is nothing but mu naught by 4 pi. I am using this one. Mu naught by 4 pi I by r, and the angle subtended by the arc at the center, which is nothing but this one. What is the angle? This is pi. So I will write here pi. So this is case 1. Okay. Suppose case 2, I ask you, suppose now my current carrying conductor is something, it is not at least circular arc. This is something, and the center is here, and the radius is this one. This is the radius. This one is also, sorry. This one is radius. What is the angle subtended? Suppose it is theta. What is the direction of the current? Suppose this is the current. What is the magnetic field at the center by the produced by this current carrying conductor? It is mu naught by 4 pi I by r, and the angle subtended by the arc at the center, which is nothing but theta. Okay. See, I can give you now a problem. Suppose the problem here, I'll just replace the theta by what? And value. Suppose it is 30 degree. And don't make this mistake. Don't write it here 30 degree only. Here we have to write mu naught by 4 pi I by r. In place of 30 degree, we have to write pi by 6. Then it will give us a final answer. If we write 30 degree, this is mistake. You know how this degree is defined, isn't it? This is not a appropriate scale. This is a comparison only. Okay. So this was all about the Biot-Savart law. There are many more applications of Biot-Savart law, but in this session I am not going to discuss. Right now I'll discuss about Lorentz force. What is Lorentz force? See, actually, Lorentz force means there are two types of Lorentz force. Lorentz force. Lorentz force. There are two types of Lorentz force. One electric Lorentz force, which is nothing but, F is equals to QE. When a charged particle Q is placed in an electric field of E, the force experienced by the charged particle is F is equals to QE. That is electric Lorentz force. And another Lorentz force is magnetic Lorentz force. This is new to us and we'll discuss about that. Okay. What is this? This is, the concept is very similar to the electric Lorentz force. When, okay, let me write in some other way. The force experienced by a charged particle in magnetic field. What is the formula for that? It is F is equals to Q times velocity cross product magnetic field. Okay, let me write here. When a charge Q is moving with velocity v in magnetic field B, then the force is F is equals to Q into V cross B. See, from this we can say one thing. Suppose a particle is in magnetic field, but at rest. What does it mean? Rest means its velocity is 0. So from this relation, F is equals to Q into V cross B, we can say the force on that particle is 0. So here we have to remember this point, that no rest particle, no rest particle can experience magnetic force or magnetic Lorentz force. This is important. From this statement, sometimes multiple choice questions is asked. Okay. But what? When there is velocity, the magnitude is what? Q into, see, V cross B. We can write V cross B when we are talking about the magnitude only. It is nothing but VB sine theta. What is theta? Theta is the angle between V, that is the velocity vector, and the magnetic field B. Okay. Now here we will discuss few special cases, that is special cases. First, suppose the theta is 90 degree. Okay, theta is 0 degree. It is important actually. Suppose theta is 0 degree. Sorry, it is 0 degree. What it gives? It gives F is equals to QVB sine 0 degree, which is again 0 QVB into 0, that is 0. So then also there will be no force on the charged particle. Okay, let me draw some. Suppose this is the direction of the magnetic field, and the charged particle is also moving in the same direction as magnetic field, sorry, as the magnetic field, that is, this is the velocity vector. So then also there will be no force. F is equals to 0. Let us consider one more angle. Theta is equals to, when it is 180 degree, then also sine 180 degree value is 0. Sine pi is 0. So then also F is equals to 0. So I suppose the velocity vector is anti-parallel to the magnetic field, then also F is equals to 0. I hope you will keep it in mind, these things, because from these concepts, these statements, usually questions is asked in many format, maybe MCQ, maybe objective, maybe in short answer type and all. Okay, then sir, for which value of theta we have the charge particle force experience force, except 0 degree and 180 degree. And for any other values of theta, it will experience force. Okay. So see, there are one more important thing, but I am not going to discuss it. Suppose theta, I'm just saying, I'll not elaborate it. Suppose theta is equals to 90 degree. Then what will happen? See, F is equals to QV sine 90 degree. The value of sine 90 degree is equals to 1. So QVB, magnitude will be QVB. What will be the direction? Just I'm telling you, suppose this is a region where there are lots of there is a uniform magnetic field. There is uniform magnetic field acting upward direction. Okay, so I hope I can copy it. I can copy it. I can copy it. So this represents a uniform magnetic field actually. This represents a uniform magnetic field. Suppose here a charged particle enter perpendicularly with velocity v, and the charged particle is charged particle of magnitude q. It enters into a large uniform magnetic field where the magnetic field is acting in the upward direction. So the force, magnitude of force is QVV only, it's constant. But the direction, what about the direction? The direction is, we get it from V cross B. V is in which direction? I cap. B is in which direction? Upward. That is out of the screen, that is K cap. So I cross K, what it gives? I cross K. I cross K. That is minus J. Minus J. If I am not wrong, let me check once. QVB. Yes, I cross K. This is I, this is J, this is K. I cross K means J only. Sorry. No. Minus J. Minus J. So the charged particle will be moving in a circular path. In a circular path. It will continuously move in a circular path. If the region is large enough, then the charged particle will be moving in a circular path. Whether it is clockwise or anti-clockwise, it will depend on the positive charge or negative charge. It will depend on that. Okay, I consider positive charge. For positive charge, it is anti-clockwise. If it is negative charge, it will be revolving in the anti-clockwise sense. Okay, so this is all about the magnetic Lorentz force and the Biot-Savart law. So I would like to conclude here. I hope you all have understood this session. If not, then do contact through my Urban Pro profile, and see you there. See you in the next session. Okay, thank you.